of this symposium. I'm pleased to be here and tell you a little bit about the work that we've been doing with trying to take some alternative approaches to producing gallium nitride substrates. What I'm going to try to do today is, first of all, give you a little motivation for why we are trying to do this. Why do we need gallium nitride substrates? And I'll actually start a little sooner than that and tell you a little bit about why gallium nitride is important. I'll then go on and talk about the characteristics of the ideal substrate, what we would like to achieve. And then I will talk about some substrate issues that are real. And I'll give you two examples of research that we have been doing to try to produce freestanding gallium nitride. One using an oxide, lithium gallate, or its analog, lithium aluminate, which is very closely lattice matched to gallium nitride as a template substrate that is easily removed, and using the relatively cheap and widely available silicon. Even though it has approximately a 20% lattice mismatch, we've been able to, through client layers, to build single crystal gallium nitride. And then I'll try to draw some physical possible. But first, I'm going to talk a little bit about why we're interested in gallium nitride. First of all, gallium nitride is a direct band gap material that happens to be just into the UV at 3.4 eV. It forms alloys with both indium and aluminum, indium being of a lower band gap and aluminum being of a higher band gap. So now we can access the full color spectrum. This is illustrated in the next slide, in which I plot the band gap energy and, of course, the visible spectrum as a function of lattice constant. The reason these two are important is, of course, the band gap energy tells us about the energy or the wavelength we might get off from a particular light-emitting device, and the lattice parameter is important for us to be able to grow high-quality material. We generally want to be able to grow structures that are well lattice matched. And so I can take gallium nitride, which is just into the UV, an alloy of indium, and you can see I can get a wide range of the visible spectrum accessible. I can also alloy it with aluminum gallium indium to form a pseudo-ternary that allows me to get this region in the spectrum as well as have a range of lattice parameters to be accessed. Some applications for gallium nitride, which was really brought to the forefront about 10 years ago when Shuji Nakamura developed his high brightness blue LED. Prior to that, he was in our laboratory with Professor Park doing MOCVD aluminum gallium nitride, arsenide. Of course, probably one of the biggest possible applications is the light emitter, both in the UV and the visible, particularly for LEDs. Solid-state lighting is a big application or potential application. Lasers are also an application. This laser pointer is an indium gallium nitride LED, a laser diode, and you can see how bright it is. It's also useful in high-density optical storage systems because we can get with shorter wavelengths and higher density storage. Full-color flat panel displays is another possible application. Because it's relatively thermally stable and has the wide band gap, it's also been proposed to be used for power devices and high-temperature electronic devices, which are actually progressing very rapidly. We talk a little bit further about the LED advantage. It is very rugged, very mechanically stable. It is lightweight. Very thin films are only required. It can be operated at relatively low voltages, 3 to 5 volts. There's flexibility in the design because of the alloying capability that we have. Lower consumption of energy compared to incandescent or fluorescent lights and monochrome. Color, temperature, and brightness are independent, and also there's a very long lifetime. So, for example, if we're comparing the LED to a fluorescent light bulb or an incandescent light bulb, you can see the lifetime is much longer. Actually, it's for continuous use, which we wouldn't use. In normal use, you might expect a LED light source to last about 20 years, whereas an incandescent bulb typically has shorter than a year of its lifetime. The energy consumption of an LED solid-state lighting source is about 5 times less than that of an incandescent bulb. So you have the potential of taking all the light bulbs and replacing them with LED-based lighting system, what is called solid-state lighting. And in doing so, you will save costs in replacement because of the longer lifetime, and you'll save costs with energy consumption because they are more efficient. And that's one of the big drivers for gallium nitride-based LED materials. So one can go, for example, and take a look at the consumption of energy to lighting applications, and these are projections for the year 2005 out to the LED penetration of the solid-state lighting market. 2005 is projected just to barely penetrate, but by 2025 it will be 55% of the world market. And if you go through the numbers and look at the energy savings and the cost per year, you find out that the energy generated capacity savings is about 125 gigawatts. And just to put that in comparison, a nuclear power plant is about 1.3 gigawatts. So the potential for energy savings is substantial if we could go to a solid-state lighting economy. Some examples of signage that you see today. This is a NASDAQ LED sign. This is looking up inside. You can see it's a very simple structure. Last night we were driving in the new south downtown area. There was a large flat panel television screen which was all based on gallium nitride. Not all now, but the blue and green were gallium nitride based LEDs. So you're starting to see it in signage. You're starting to see it also in your stoplights and your exit signs. The reason is because the long lifetime of LEDs will prevent, first of all, the maintenance. The stoplights have to be changed out and the exit signs very frequently, because if a light burns out, then you have a safety problem. Furthermore, there is also, they last for a long time, so very improbable that they will burn out and cause that safety hazard. And as a result, that's some of the first applications that are being used today for LEDs. Well, why do we need gallium nitride wafers? Today, most of the gallium nitride LED devices are grown on predominantly sapphire and to a lesser extent silicon carbide. And devices that are made from them are very bright. They're particularly LED devices, and but there are some issues that remain. One has to do with wafer scale-up. The mismatch between sapphire and, to a lesser extent, silicon carbide is extreme, 16% for sapphire. And that thermal stress will cause the wafer to bow. And that bowing will cause subsequent processing, device processing, to be more difficult. Furthermore, the sapphire is not conducting, so both contacts have to be made from the top side. That requires more use of real estate. Therefore, you get fewer die per chip. The stress, the bowing, limits us now to about a 2-inch or 100 millimeter wafers, or 50 millimeter wafer size. So as a result, again, our throughput will be low. And the reason we don't have solid-state lighting now is because of cost. The diodes today cost about, they're on the order of 10 to 15 cents a diode. And to get the brightness for the light bulb, you need to put together on the order of about 20 diodes. And so the cost gets prohibitive. If we can get the manufacturing costs down, you'll see that penetration of the solid-state lighting market occur faster. There's also a problem with defects. Even in the very best sapphire-grown gallium nitride, the defect density is on the order of 10 to the 8th dislocations per square centimeter. And that's a very high dislocation density, particularly if you're doing laser applications. And so, surprisingly, the material works as well. Other compound semiconductors will not produce as good a quality material with that high defect density. There's also, I mentioned, the conductivity control. Sapphire is insulating. Silicon carbide has a problem being doped P-type. There is also other improved properties. The breakdown voltage for some substrates is a problem. Thermal conductivity needs to be high for some applications, particularly power devices. You need to have thermal, mechanical, chemical stability, which can be an issue with some other substrates. You need to have radiation hardness if you're going to talk about space applications, etc. So there is a need for gallium nitride substrates, and folks in many laboratories are trying to produce large area freestanding gallium nitride. Well, if I had my wish, I would have an ideal substrate. First of all, I would have a large area. That would allow production of a large number of die per wafer, high throughput, lower the cost. I would have a variable or a lattice constant that would be well matched to gallium nitride or what alloy that I was trying to grow as my base material. I would have good chemical, thermal, mechanical stability, of course. I would have high conductivity, both thermal and electrical, and I'd like to control it either P or N type. I need the thermal conductivity to get rid of the waste energy. I would have dislocation-free films because dislocations serve as recombination centers, non-radio recombination centers, and therefore decrease the efficiency of my device. I would like to have the lattice constant be variable so I could tune in the wavelength and correspondingly adjust the substrate material. I would like to have it to be transparent in UV because if I'm going to replace the fluorescent bulbs, which I have here, I'll likely want to have a UV LED source. And I would, of course, want to have easy ohmic contacts that have very low resistance, contact resistance, to again minimize the energy generated. Unfortunately, we don't have that substrate, but there are some things that are issues that we must overcome. We have no suitable large area substrate at this point in time. We are stuck with 2-inch sapphire and very expensive silicon carbide. The large mismatch that exists between those two substrates, the gallium nitride gives a 10 to the 7th, 10 to the 8th dislocation density, which for some devices is unacceptable. The electric conductivity is not controllable. As I said, sapphire is an insulator. Some of the alternative substrates besides those two have problems with both chemical and thermal stability. And for devices such as lasers, where I need cleavage planes, sapphire doesn't have them available, and so I have some issues there with just respect to device processing. I could have etching problems, I have contact problems, etc., in terms of subsequent device processing. So, it doesn't look too good. Well, how have people tried to get around this problem? And there's basically two approaches. One is heteroepitaxy. That is, I'm going to grow gallium nitride on a foreign substrate. The second approach is homoepitaxy. That is, I'm going to grow gallium nitride on gallium nitride, but I've got to produce the gallium nitride substrate. And there's two ways to produce the gallium nitride substrate. Of course, the easiest way is what we do with silicon, is to produce it from the bulk, or silicon carbide, or sapphire. We just produce it from the bulk. And we can either produce it from the melt, as in silicon, or from solution, as we do with some oxide crystals, or from the vapor phase, for example, sublimation growth, as we do in silicon carbide. Unfortunately, as I'll show you in a second, gallium nitride has some difficulties with growth from the bulk. Most of the attempts that we've been doing to date, the ones that got us to this point, have been the heteroepitaxy growth. And in particular, we've used sapphire plus silicon carbide, and to a much lesser extent, these substrates. These have been relatively unsuccessful to date. We've done it by using a low temperature buffer layer to allow us to have a layer in between the substrate and the gallium nitride to serve as a nucleating grain growth area to allow single crystal gallium nitride to be grown at large mismatch, but with large dislocation density. We've improved on the dislocation density by several tricks. One, probably most popular, is to do lateral overgrowth. That is to open windows into a mask and have deposition occur selectively in the window openings and not on the mask material. As the material, the gallium nitride, grows selectively in those window areas, it will eventually exceed the height of the mask and then grow laterally and eventually join each other. And that area over the mask material is relatively dislocation-free. That has problems too with limited use of area. There's problems where the material meets, but it is the material choice for the laser diode fabrication that occurs today. What I'm going to talk about today is this side here. To do homoepitaxy on gallium nitride, but to grow gallium nitride very thick onto a removable substrate. So we're just going to take a substrate that's well lattice matched, use it for a template, grow very thick gallium nitride, 200 microns or so, and then remove the substrate to produce and leave behind freestanding gallium nitride. And I'm going to tell you about two techniques we've been using. One is using the lithium aluminate or lithium gallate, which is closely lattice matched to gallium nitride. And another approach is some advances we've had, or some good luck we've had with using silicon and a compliant layer that is relatively easy to form. Both of these materials have produced single crystal freestanding gallium nitride. And what I'm going to talk about for the remainder of this talk is this particular substrate. Now, there are a variety of ways to grow thick gallium nitride. And the traditional epitaxial techniques are relatively slow growth rate. MOCVD and molecular beam epitaxy are relatively low growth rate. We need a high growth rate process. And I'm going to talk specifically about hydride vapor phase epitaxy, although there is work going on elsewhere on liquid phase epitaxy, sublimation growth, and plasma jet processing. We then have to remove the substrate. And one way to remove the substrate, for example, is to ablate the substrate away. Of course, you destroy your substrate. If it's expensive and it's not reusable, it's removable but not reusable. Another way is to etch it. Again, that's a destructive removable technique. Another way is delamination, which is non-destructive. That is, we can get it to separate it. And I will show you that we were able to, with lithium aluminate and lithium gallate, able to achieve self-separation. That is, they would separate upon cooling due to the thermal stress, the mismatch of thermal expansion coefficients produce a stress that caused and promoted the delamination. With the silicon is very cheap for the substrate, and it's very easily removed, etched selectively relative to gallium nitride. So it can serve easily as an sacrificial substrate. Okay? So that's kind of the outline of what I'm going to talk about. Just to show you, though, on the high pressure side, the difficulty of growing gallium nitride from the solution. Here's a phase diagram that we calculated for gallium nitride. You can see it melts at about 2,500 degrees C, making bulk crystal growth very difficult. There is also a liquid-liquid miscibility gap that exists here, and so if you're not right on solution, or your nitrogen leaves from the vapor pressure, you can see you can very easily pull over to there or get off stoichiometry. Furthermore, the solubility of nitrogen in gallium is very, very low. So if you wanted to grow at, say, 1,200 degrees C, you only have on the order of 100 or so parts per million solubility of nitrogen in gallium. Therefore, the pool of gallium, which is relatively expensive, that you would have would be extremely large to give any significant growth of gallium nitride. In addition to that, the vapor pressure at, say, 1,300 degrees C is on the order of several kilobars. So you would need a very expensive high-pressure chamber to be able to do that. For that reason, I don't think high-pressure, high-temperature solution growth is going to be a viable process, although people are still working on it. So the approach that we're going to talk about again, first of all, is the lithium aluminate, and then I'll talk about the silicon growth. Possible substrates, here are some common ones. The two I'm going to talk about first are lithium aluminate, lithium gallate, and you can see that here are the lattice parameters for gallium nitride. And it turns out that the pretty good match here with lithium aluminate and also with lithium gallate, less than 1%. Thermal expansion coefficients are also fairly well matched. Silicon, however, which I don't have, I'm going to come back to that later. Before I do that, I'm going to tell you, in our work, we use two different growth chemistries. We use a traditional MOCVD, I'll talk a little bit about that, and then we use hydride vapor phase epitaxy. The MOCVD was low growth rate. It was used for capping layers and barrier layers. The hydride VPE was used for the film growth. Okay. Here is a typical IMCOR type reactor. It's a rotating disc. We have flow down and out, very uniform mass transfer except for the boundary or the edges. The metal organic, for example, trimethylgallium, is mixed with ammonia in an injector head, and actually they have to be mixed at the right point because there's an attic formation that occurs. These are then impinged onto this heated substrate, and the reaction of trimethylgallium with ammonia to give gallium nitride occurs on the surface. That's a simplistic view of what's going on. A more accurate description of the chemistry that takes place for gallium nitride deposition involves ammonia and trimethylgallium as your precursors. Ammonia will thermally decompose to give NH2, being the rate limiting step. Once you form the NH2, you very rapidly go to further products. This reaction has been fairly well studied. Trimethylgallium will undergo homolytic fission sequentially to give dimethyl, monomethyl, and then gallium, which can occur in the gas phase. This step is relatively rapid from dimethyl to monomethyl gallium, and we have observed monomethyl gallium as well as elemental gallium in the gas phase. The problem with trimethylgallium and ammonia and our difficulty prior to 1992 of being able to achieve MOCVD of high quality gallium nitride was the fact that trimethylgallium will form an addict with ammonia. And this addict then can further polymerize to form an oligomer. This oligomer will essentially take the gallium out of the reaction. The oligomer can form by an intermolecular mechanism. Oh, my laser just shut. And back to the gallium arsenide base. I'll gas laser. It can form by an intermolecular route, or it can also form, we believe, by an intramolecular route. The kinetics of these reactions are not known. In fact, this reaction was only postulated. So one of the first things we looked at was to try to study the kinetics of this process. And we did so in an impinging jet reactor. What this is a set of quartz flat. We have a laser beam that will come in and focus down to a 30 by 30 by 300 micron region. And then we'll look at the 90-degree scattered light from that. And that will give us a signature for the molecule by looking at the vibrational or possibly the electronic spectra, Raman spectra of the molecules in that volume. By looking at the rotational spectra of our carrier gas, we can also estimate quite accurately, within about 10 degrees, the temperature locally. This whole reactor is mounted on XYZ stage, so we can actually move the reactor and sample different positions. So a heated susceptor, an impinging flow, we're able to measure the center line composition and temperature profile, from which then we can look at the species present and back out rate constants and try to understand the chemistry. So as a first study, just as an example, we looked at ammonia decomposition in nitrogen. This is the temperature profile in our reactor. The yellow data here is actual measurements of the ammonia concentration. The black line is one that includes a surface reaction plus gas phase reaction and gas phase dispersion in a model. We invert that model and are able to estimate the rate constants, and we come up with a free exponential as indicated here at 90 kcal per mole activation energy, which compares very well with that recorded in the literature. So this serves as a check that our system is working well. We then go on and look, and we intentionally formed this addict. We mixed ammonia with trimethylgallium, deposited out in excess in a packed bed, and then flew just ammonia nitrogen over that to form a saturated solution of trimethylgallium ammonia addict. What you see here is the green is, and what we're doing is measuring the concentration from the inlet to the surface. So we see the addict coming in, and once it reaches a certain temperature, which is indicated about right here, you see that the addict starts to disappear. As the addict disappears, we start to form trimethylgallium. The formation of trimethylgallium then will attack the addict and form the oligomer. And you see now the oligomers start to form. So that verifies that that intermolecular pathway is indeed operative. Going one step further, if we now put in trimethylgallium separate from ammonia, separate from nitrogen, as you do in a traditional MOCVD reactor, you can see we form upstream very quickly the addict trimethylgallium ammonia, but since there's excess trimethylgallium around, we can react it to start to form the oligomer up front. Then the addict starts to reversibly go back to decompose, to go back to trimethylgallium and ammonia. The more trimethylgallium starts to appear, it starts to react and we form even more oligomer. And so the key to designing this reactor is to prevent the formation as much as possible of the oligomer and to deliver as much as you can of the trimethylgallium right at the surface so it can be reactive. And this is what that cross-flow design that Nakamura came up with did effectively, and what the new reactor design do effectively as well. So, with that, we have an ability to grow high-quality, slow growth rate, MOCVD gallium nitride, but we also need a high-rate growth mechanism. And we're going to use hydride vapor phase epitaxy, which is very simple. We take ammonia, a hydride source, and we take HCl, react it with liquid gallium to form volatile gallium chloride. And then the gallium chloride and ammonia are mixed, and in the heated deposition zone will react to form gallium nitride. It will reduce the gallium chloride and give a byproduct of HCl and hydrogen. A very simple process. The key advantage here is that it can be grown at high growth rate. We have a slightly modified version of this. What we do is we inject HCl, and instead of reacting with gallium liquid, we react it with trimethylgallium. And the reason we do that is because we can turn the HCl off and have traditional MOCVD, or we can very rapidly switch the trimethylgallium on and off, or indium, or aluminum, and this way we can get very rapid switching of our three source, and therefore we can grow quantum well structures. But this is the system, the hydride system that we operate. The chemistry, however, beyond this region, beyond the source zone, is identical to hydride PPE. That is, we have gallium chloride and ammonia combining to deposit gallium nitride. And we've studied the growth chemistry of it. Most of the deposition we're going to be doing is in the mass transfer limiter regime, although on the silicon we're going to show you some work that's at low temperature in a reaction limiter regime. Okay, back to the problem of growing freestanding gallium nitride. We're going to talk about in detail the lithium gallate. It's an orthorhombic structure that's very close to the hexagonal structure of gallium nitride with about a 0.9% lattice mismatch. One of the problems with lithium gallate, though, is it is attacked by hydrogen. And we have hydrogen in our system, if nothing else, from decomposition of ammonia. Lithium gallate, when we started on this, there was no experience in growing it. There was no substrates available. We teamed up with Bruce Chai at the University of Central Florida, who was a bulk crystal grower and was growing this material. We discovered very early that there was problems with stability of the substrate. That is, it will react with gallium nitride, which we're trying to deposit on it. Or we weren't sure, but it was a possibility. We discovered that hydrogen and HCl would attack it very easily, and we wondered whether lithium would out-diffuse and enter into the gallium nitride where it would be electrically active and a relatively fast diffuser. We also had some issues with how to grow thick gallium nitride on the material, which we've resolved and I'll talk about. And then what about, once we grow the thick gallium nitride, how do we remove the lithium gallate? So these were the issues in our mind before we started the actual experiment. Now, the process we came up with to grow freestanding gallium nitride is illustrated here. We take single crystal lithium gallate. We had, again, 50 millimeter wafers, single crystal material. We would grow a reaction layer. It's really a nitridation of that surface at about 800 degrees C for 10 minutes. that would grow a 50 to 100 angstrom silicon, or not silicon, but a lithium gallium oxynitride. And I'll talk a little bit about that. We would then grow by MOCVD, a gallium nitride buffer layer. And that was really a protection barrier material to keep the hydrogen HCl from hydride BP away from the lithium gallium. And we grow on the order of 2,000 to 3,000 angstroms of materials. We then go our very high rate, on the order of 70 microns per hour, growth by hydride BPE to grow to 1 to 300 microns thickness of gallium nitride. We discovered, however, the surface that we would grow there was very rough. We also discovered that that surface was very reactive and thermally unstable. And as a result, we, by chance, grew a capping MOCVD layer of gallium nitride, and were able to recover surface smoothness and thermal stability. And I'll tell you a little bit why. But that's our basic process. So I'm going to step through these and just give you a few results at each step. Okay. First step was to take as received lithium gallate, and an as received material. This is a cross-sectional TEM micrograph, and this is the region here near the surface. You can see the near surface regime was not single crystal. It was amorphized. You will also see from this AFM micrograph that it was relatively rough, even polished. We had to learn how to polish it, but even so, it was still relatively rough, 3.5 or 3.4 nanometer roughness. However, if we nitrided the surface by exposing it to ammonia at an elevated temperature, this resulted for 850 degrees C, you see that this region near the surface recrystallized and became single crystal. You'll see the surface smoothed on it to essentially a spectral surface. And according to this OJ spectra here, you'll find that there's nitrogen content after nitridation. So that surface chemical composition was a lithium gallium oxynitride. And we estimate about 15% nitrogen. But this recrystallization was probably a key step to being able to grow high-quality gallium nitride. And then having this oxynitride being a compliant substrate relative to the underlying lithium gallate was also important for the growth of high-quality gallium nitride. We also did some anneal studies afterwards and determined that the lithium interdiffusion was not a problem. That the lithium diffusion through that barrier layer was very slow. We estimated it on 10 to the minus 17th centimeters squared per second. Here are some MOCVD growth results then growing on top of that nitrided layer. You can see here is an AFM micrograph of the gallium nitride growing, very smooth surface. This is a high resolution X-ray diffraction spectrum showing a full width path max of about 21 arc seconds. That's as high a quality of gallium nitride has been reported. And it was typically in-type material, but we were able to, and here's a cross-sectional TEM micrograph showing, picked up a dislocation here, but it's relatively clean. We estimate it to be about 10 to the 7th per square centimeter material. But it's relatively high-quality gallium nitride, growing relatively easy at a low temperature of 850 degrees C. So we then would take this layer and grow a thick gallium nitride on top of it using hydride BPE. So we're going to grow this thick layer using the hydride BPE. And whether we cap it off with gallium nitride MOCVD or not, we found that when we would cool it, that it would pop off. It would self-separate. It would delaminate. And we suspect it was the thermal stress that developed upon cooling that provided the force for the delamination. And here's an example of a 10 by 10 millimeter freestanding piece of gallium nitride. Turns out, too, when you take a look at the gallium nitride and the separated lithium gallate, it's separated at the gallium nitride oxynitride interface. So the substrate is completely reusable. And you just keep growing, self-separate, put it back in, grow again. The material had about a 50 arc second full width half max thickness, which again is high quality material. the composition was very uniform by Auger. Again, we had, as I told you, we found we had got very smooth results in the surface, and we also got a more thermally stable material if we grew this capping MOCVD layer. Here are some AFM images. Very smooth surface if we used a cap, rough surface if we did not. And here's the thermal stability studies. This is we're taking the gallium nitride to 965 degrees C in an HCl environment, very attacking environment. Here's the hydride DPE material, thermally decomposed very easily, whereas the MOCVD material, capped on it, both of them pure gallium nitride, showed a little bit, and we really had to look for a bad spot, surface roughness due to sublimation. Subsequently, we have done some experiments that lead us to believe the difference between the hydride and the MOCVD gallium nitride is one of polarity. This material is gallium terminated, this material is nitrogen terminated. And so the only difference between the material is that when you take a piece of gallium nitride on a C plane and split it, you end up with one wafer that is all gallium terminated and another that's all nitrogen terminated. And it's the gallium terminated surface that goes smoothly, that has a high thermal stability with some activation energy to decomposition. All right. We also worked on lithium aluminate, and we've been able to see similar results, actually slightly improved results. And I won't go into the details there, but just to compare them, we did get freestanding in both. But the lithium aluminate is more stable than lithium gallate. It's also more chemically stable, particularly with respect to hydrogen attack. It had improved mechanical stability in its freestanding forms. That is, we were able to get a lower stress state off the lithium aluminate. The background carrier concentration was lower in the material as well. And it had a higher degree, it was transparent, whereas the lithium gallate sometimes would have oxygen-related, we believe, yellow consistency to it. Okay. I'm going to spend just a couple minutes talking about what we've been doing more recently with silicon, because if we can grow high-quality gallium nitride on silicon, we've got a very cheap, disposable substrate that is large area. Or we could just retain the substrate and grow directly. The advantage of silicon, as I said, are the low cost, large size, high quality, etc. The biggest disadvantage is the 20% lattice mismatch. Well, we tried to do exactly what we did with the aluminate and the gallate. We tried to take the silicon and nitride the surface. So we took 850 degrees C and ammonia, and we grew it, and we get polycrystal material. Well, it turns out when you nitride silicon, it forms an amorphous silicon nitride interfacial layer, and that amorphous layer is not conducive to growing single crystal gallium nitride. So we backed off and we went to look at the phase diagram. Good chemical engineers always look at phase diagrams, and material scientists. And what we discovered was that if we were above about 560 degrees C, we always had a stable silicon nitride phase. But if we got below that temperature, we had only gallium nitride and silicon dioxide being the stable phases. So we tried dropping the growth temperature down to about 550 degrees C to see what would happen. And lo and behold, growing to 560, actually slightly below that, we were able to get single crystal gallium nitride on 2-inch silicon. And here's an AFM image. It's relatively smooth surface, particularly for growing on silicon with a large mismatch. Here's a cross-sectional TDM micrograph showing the silicon, the compliant SiO2 layer, the buffer MOCVD we put on it, and the subsequent hydride thick VPE layer. Here is a cross-sectional TDM of it, and it shows indeed it's single crystal. It's got a higher dislocation density than what we have with the lithium aluminate or lithium gallate, but it too will self-separate on cooling. So we can grow freestanding gallium nitride. We've also been working with aluminum nitride buffer layers, and again, we've been able to achieve our highest quality gallium nitride with that particular buffer layer. So, In conclusion, silicon nitride, I believe we've made some very good progress with growing high-quality gallium nitride on silicon, as illustrated here. Where is it going to go? I mean, Volt's crystal ball. I think we're going to end up with different approaches for different applications. I think some dislocation-tolerant device applications such as LEDs, which are currently using primarily sapphire. I think we will go to silicon or possibly freestanding gallium nitride if it becomes cheap enough. The dislocation-intolerant devices such as laser diodes, we're currently using the lateral overgrowth on sapphire. I think we'll probably go to improved selective area growth techniques on alternative substrates. The electronic high-power, high-temperature devices will probably also go to silicon carbide, which has some good thermal characteristics to it, and good breakdown voltage, or the freestanding gallium nitride once it becomes available. So 10 years ago, solid-state lighting and other applications were really just an illusion. We could not get blue. Blue was missing. And hopefully this illusion no longer exists, and we now have blue skies, or blue lighting ahead of us. So with that, I'd be happy to entertain any questions, and Kamsa Hamza.